The wind cut different across the Nebraska prairie in winter, 1884. Thomas Mackay learned that his first February when ice formed inside his cabin walls and his water bucket froze solid 4 feet from the wood stove. He had built his cabin exactly like every homesteader on the Great Plains was told to build it. Tight log walls, stone chimney rising straight up, standard wood-burning stove, trusted and proven. By March, he had burned through 3 full cords of driftwood and still woke to 15-degree temperatures inside, while neighbors fought the same losing battle in cabins built by the book and failing by the season. Over the next 2 years, Mackay quietly borrowed techniques from Old World masonry and indigenous building methods to create a heating system that kept his cabin warmer while using half the firewood. His neighbors called his buried chimney design foolish and wasteful. But when the brutal winter of 1890 hit, Mackay's unusual system held steady at 50 degrees, while standard cabins dropped to freezing. This video breaks down the exact principles and measurements behind his impossible results. What did this Scottish stonemason understand about capturing heat before it escaped that every frontier builder missed? The standard frontier heating method dominated the Great Plains for good reason. Every homesteading manual from Kansas City to Omaha recommended the same approach. Build your cabin with tight log walls, raise a stone chimney straight up through the center or against one wall, install a cast iron wood-burning stove with a direct flue connection, and stack plenty of cordwood nearby. Local builders like Mr. Anderson had constructed dozens of cabins this way throughout the Platte River region, following techniques their fathers used back east and trusting methods that seemed both familiar and economical. The approach made perfect sense to settlers arriving from timber-rich regions. A tall chimney created strong draft to pull smoke up and out. The direct flue connection meant simple installation with minimal labor. Most importantly, the materials were readily available: field stones for the chimney base, local timber for framing, and cast iron stoves shipped by rail from foundries in Chicago and St. Louis. Every supply barn stocked the standard components, and every local mason knew how to stack a straight chimney that would draw properly and last through prairie winters. But the prairie environment punished this Eastern wisdom in ways the manuals never anticipated. The relentless winds that swept across the open grassland created draft patterns that pulled heat straight up the chimney faster than the fire could replace it. The expansive sky and flat terrain meant no natural windbreaks to shelter cabins from the constant air movement that sucked warmth from every gap in the walls. Most devastating of all, the ground froze to depths of 4 feet or more, creating a massive heat sink beneath every cabin, floor that drew energy downward while the chimney pulled it upward. Mackay's neighbors within a mile radius of his homestead experienced identical struggles that first winter of 1885. The Johnson family to the east burned through 4 cords of driftwood and still recorded interior temperatures dropping to 18 degrees on the coldest January nights. Mrs. Anderson, wife of the local builder, complained that her kitchen floor remained so cold she could see her breath while cooking breakfast, even with the stove blazing. The Swedish immigrant Eric Svensson, whose family had experience with harsh winters in Minnesota, found his Nebraska cabin demanded twice the fuel his previous home required, despite using the same construction methods. The mechanical problems went beyond simple heat loss. Chimney draft patterns created pressure differences that pulled cold air into cabins through every chink and gap in the log walls. The tall stone chimneys accumulated creosote rapidly in the fierce cold, requiring frequent cleaning to prevent dangerous buildup. When temperatures dropped below 0 degrees Fahrenheit for extended periods, chimney tops often froze partially closed, creating backdraft that filled cabins with smoke and forced families to extinguish their fires at the worst possible moments. Thomas Mackay brought unique knowledge to this common frontier problem. His apprenticeship as a stonemason in the Scottish lowlands had exposed him to heating methods that predated the simple stove and chimney combination. In the border country, he had observed massive stone fireplaces with complex flue arrangements that captured heat in the masonry before allowing smoke to escape. More importantly, he had spent time with Highland builders who constructed bothies, simple stone shelters that used underground channels and earth berming to retain warmth with minimal fuel. During his first difficult winter, Mackay began conversations with local craftsmen who carried knowledge from other traditions. The German immigrant Johann Müller described the Kachelöfen heating systems common in Bavaria, where exhaust gases wound through labyrinthine passages in massive masonry stoves before exiting, transferring most of their heat to stone that radiated warmth for hours after the fire died. Erik Svensson shared Scandinavian techniques for breaking the cold connection between cabin floors and frozen ground using layers of crushed rock and raised foundations. Most significantly, Mackay developed a working relationship with white pine, a Lakota carpenter whose people had survived Great Plains winters for generations before European settlement. White pine explained how traditional winter lodges incorporated partially excavated floors lined with flat stones that absorbed heat from small fires and radiated it back slowly. He demonstrated the use of earth berms piled against lodge walls to deflect wind and reduce heat loss through the structure itself. The social. Friction began when Mackay proposed combining elements from these diverse traditions into his standard cabin design. At the local supply barn where homesteaders gathered to discuss building projects and share experiences, Mackay described his plan to route his stove's exhaust through a stone-lined trench beneath his cabin floor before connecting to the chimney. The established builders dismissed the idea as unnecessarily complicated and potentially dangerous. Mr. Anderson, whose reputation rested on successful completion of dozens of conventional cabins, argued that underground flues would accumulate moisture, create fire hazards, and require maintenance that ordinary settlers could not manage. Other neighbors suggested that Mackay was overthinking a simple problem that could be solved by burning more wood or improving the cabin's chinking. The general consensus held that proven methods should not be abandoned for untested experiments, especially when failure could mean death during a severe winter. Mackay proceeded with his modifications despite the skepticism. During the summer of 1886, he excavated a trench approximately 15 feet long and 8 inches wide beneath his cabin floor. He lined this channel with field stones, creating a pathway for hot exhaust gases to travel horizontally under the floorboards before rising to the chimney. The excavated earth was mixed with crushed stone and packed back around the lined trench to create thermal mass that could absorb and store heat. The initial installation represented only part of Mackay's envisioned system. He recognized that capturing heat beneath the floor addressed just one aspect of the thermal losses that plagued frontier cabins. The walls and ceiling still leaked warmth, and the chimney draft still pulled heated air out faster than necessary. But the underground flue component would serve as the foundation for additional modifications he planned to implement based on the results of his first winter trial. The first winter with the underground flue trench revealed problems Mackay had not anticipated. While the buried stone channel successfully captured some exhaust heat before it reached the chimney, precise temperature measurements exposed a more fundamental issue with frontier cabin design. Using a mercury thermometer borrowed from the local doctor, Mackay discovered that his cabin floor surface registered 30 degrees Fahrenheit at dawn, even when the interior air temperature measured 45 degrees. The floor itself was acting as a massive heat sink, drawing warmth downward into the frozen prairie soil. Traditional frontier construction ignored the thermal properties of ground contact entirely. Most homesteaders laid their cabin floors directly on packed earth, or placed them on simple timber sleepers with minimal insulation underneath. The Nebraska soil froze to depths exceeding 4 feet during severe winters, creating an enormous reservoir of cold that continuously pulled energy from any structure in contact with it. Mackay calculated that this ground loss accounted for roughly 8% of his total heating energy each night, based on careful tracking of his wood consumption and interior temperature drops. The solution required expanding beyond the single buried flue to create a comprehensive thermal mass system beneath the cabin. Erik Svensson provided the first piece of this puzzle during a visit to Mackay's homestead in late spring of 1886. The Swedish immigrant had built several cabins in Minnesota using techniques from his homeland, where builders routinely place 6 inches of crushed stone and tamped earth beneath floor structures to break the direct cold connection with frozen ground. Svensson explained that Scandinavian log homes incorporated what he called thermal barriers, layers of different materials that slowed heat transfer and created insulation between the living space and the earth below. The crushed stone provided drainage and prevented moisture problems, while the compacted earth above it stored some heat and released it slowly. Most importantly, this foundation system raised the actual floor surface temperature by creating a buffer zone that prevented direct thermal contact with the deep, frozen soil. Red Bear, a Lakota elder who occasionally worked as a carpenter for local settlers, contributed knowledge from an entirely different tradition. His people had survived Great Plains winters in earth lodges that incorporated partially excavated floors lined with flat stones. These stone floors absorbed heat from small fires during the day and continued radiating warmth throughout the night, maintaining comfortable temperatures with minimal fuel consumption. Red Bear demonstrated the principle by examining McKay's cabin floor with his hand, pressing his palm against different sections to feel temperature variations. He explained that stone held heat much longer than wood or earth, and that the key was creating enough thermal mass to store significant energy while ensuring that mass remained in contact with the living space rather than the cold ground below. McKay spent the summer of 1886 implementing a hybrid system that combined elements from both traditions. He excavated the area beneath his entire cabin floor to a depth of 8 inches, far beyond what the original flue trench had required. The bottom layer consisted of 4 inches of crushed limestone and fieldstone, carefully graded and compacted to provide drainage and insulation. Above this, he placed 2 inches of packed earth mixed with smaller stones to create a dense thermal mass that would absorb and store heat. The buried flue trench remained the central component, but McKay extended it laterally beneath a low stone wall he constructed inside the cabin along the north side. This interior wall, built from limestone blocks and standing 3 feet high, served multiple purposes. The extended flue channel allowed exhaust gases to travel beneath this massive stone structure before reaching the vertical chimney, transferring additional heat into the thermal mass. The wall itself became a heat bank, absorbing warmth during fires and radiating it back into the living space for hours afterward. The construction required precise attention to structural details. McKay lined the extended flue passages with fitted stones to prevent heat loss into the surrounding earth and installed removable stone covers at several points to allow cleaning and maintenance access. The thermal mass wall incorporated channels that connected with the underground flue system, ensuring that hot exhaust gases could warm the entire stone structure rather than just the section directly above the buried trench. During the winter of 1886 to 1887, McKay conducted systematic measurements to evaluate the thermal mass system's performance. He recorded interior temperatures at dawn, midday, and midnight, tracking both air temperature and floor surface temperature throughout the coldest months. The results exceeded his expectations and validated the combined approach he had developed. Wood consumption dropped dramatically from the 3 cords he had burned the previous winter to approximately 1 cord and 3/4 for the same period and occupancy. More significantly, floor surface temperature at dawn improved from 30 degrees Fahrenheit to 45 degrees, eliminating the cold shock that had previously made morning activities uncomfortable. The interior air temperature stabilized at 50 degrees Fahrenheit at dawn, compared to the previous winter's 45-degree readings. The thermal mass wall proved especially effective during the severe cold snap in February, when outside temperatures dropped to minus 20 degrees Fahrenheit for 6 consecutive nights. While neighboring cabins struggled to maintain interior temperatures above freezing, McKay's system held steady. The stone wall remained warm to the touch throughout each night, continuing to radiate stored heat long after the fire had burned down to coals. McKay's neighbor to the east, still using a conventional cabin design, burned 2 full cords of wood during the same February period and recorded morning floor temperatures at 28 degrees Fahrenheit. The difference became obvious to anyone who visited both cabins. McKay's floor felt comfortable barefoot even in early morning, while conventional cabin floors required thick wool socks or slippers to avoid discomfort from the cold surface. The thermal mass system also improved air quality inside the cabin. The stone wall and thermal floor reduced the temperature differential between floor and ceiling, minimizing convection currents that had previously stirred up dust and created drafts. The more stable temperatures meant less expansion and contraction in the cabin's wooden components, reducing gaps that allowed cold air infiltration and eliminating many of the whistling sounds that characterized poorly heated frontier dwellings during windy nights. By spring of 1887, word of McKay's reduced fuel consumption had spread throughout the local homesteading community. The dramatic difference in wood usage represented significant savings in both labor and cost, particularly important for families who had to haul their fuel long distances or purchase it from suppliers during severe weather. The success of the thermal mass floor system revealed a new set of problems with conventional frontier cabin construction. During the winter of 1887, Mackay used his mercury thermometer to map temperature variations throughout his cabin's interior, discovering that heat stratified dramatically between floor and ceiling. While his improved floor now maintained 45 degrees Fahrenheit at dawn, the ceiling surfaces measured only 35 degrees, creating a 15-degree temperature gradient that indicated massive heat losses through the upper portions of the cabin envelope. Standard frontier cabin walls consisted of single-thickness logs with simple chinking, offering minimal thermal mass to absorb and store heat from the interior. The hot air generated by Mackay's stove rose immediately to the ceiling area, then cooled rapidly as it contacted the cold log surfaces and leaked through gaps in the chinking. This cooled air descended along the walls, creating convection currents that continuously pulled heat away from the occupied zone near the floor where his thermal mass system was most effective. The problem extended beyond simple heat loss to fundamental issues of comfort and fuel efficiency. Mackay noticed that family members consistently gathered within 3 feet of the stove, even with his improved floor system, because the wall surfaces remained uncomfortably cold to the touch. The cabin's corners, where 2 exterior walls met, became particularly frigid zones, where frost sometimes formed on the interior wood surfaces during the coldest nights. Johann Müller provided crucial insight into solving these envelope problems when he visited Mackay's homestead in spring of 1887. The German immigrant had constructed several masonry stoves in Bavaria that incorporated what he called thermal mass walls, where the combustion chamber was surrounded by thick stone or brick construction that absorbed heat from the fire and radiated it slowly into the living space. Müller explained that European Kachelofen designs routed exhaust gases through channels built into massive masonry walls before allowing the gases to exit through the chimney. These wall passages, called labyrinth flues, extracted additional heat from the combustion products while charging the surrounding stone with thermal energy. The result was walls that remained warm to the touch for hours after the fire died, providing radiant comfort that heated people directly rather than just warming the air. Mackay recognized that he could adapt this principle to his existing cabin by adding an interior stone lining to his walls and routing his underground flue system through passages behind this new thermal mass. The concept would integrate with his floor system to create a comprehensive thermal envelope that captured heat throughout the cabin structure rather than allowing it to escape through cold surfaces. White Pine contributed additional knowledge about envelope insulation when he examined Mackay's cabin walls during a summer visit. The Lakota craftsman demonstrated techniques for improving chinking between logs using split cedar bark, which provided better insulation than the clay and moss mixture most settlers used. More importantly, he explained how earth berms piled against exterior walls could dramatically reduce wind-driven heat loss. White Pine showed Mackay how his people constructed winter shelters with earth walls built against the exterior structure on the sides that faced prevailing winds. These berms, typically 2 to 3 feet high, created dead air spaces that prevented cold wind from directly contacting the building envelope. The earth mass also absorbed solar heat during sunny winter days and released it slowly, moderating temperature swings around the structure. During the summer of 1887, Mackay implemented a comprehensive envelope upgrade that combined elements from both traditions. He constructed an interior stone lining 4 inches thick along all exterior walls using limestone blocks fitted closely together and secured with lime mortar. This lining created approximately 4,000 pounds of thermal mass distributed throughout the cabin's interior surfaces. The critical innovation involved extending his underground flue system vertically behind these new stone walls. Mackay built narrow channels approximately 4 inches wide between the original log walls and the new stone lining. His buried flue connected to these vertical passages, allowing hot exhaust gases to rise behind the thermal mass walls before finally reaching the existing chimney. The system created a heat exchange network that warmed the stone walls throughout their height, rather than just at floor level. Construction of the wall channels required precise stonework to ensure proper gas flow while maintaining structural integrity. Mackay installed removable inspection plates at several points along the vertical flue passages and incorporated draft controls that allowed him to regulate the flow of exhaust gases through different sections of the wall system. The channels included expansion joints to accommodate thermal movement of the stone during heating and cooling cycles. On the exterior, Mackay built earth berms along the cabin's west and north sides, where winter winds were most severe. These berms rose 2 feet above ground level and extended 3 feet from the building, using excavated soil mixed with stones for stability. He planted prairie grass on the berms to prevent erosion and create additional insulation through the root system and dead vegetation. The envelope system integration required careful coordination with the existing floor thermal mass. Mackay designed connection points where the vertical wall flues drew heated air from the underground system, creating circulation patterns that distributed warmth throughout the stone mass. The system functioned as a continuous thermal circuit, with hot exhaust gases warming first the floor thermal mass, then rising to heat the wall mass, before finally exiting through the chimney. Testing began immediately with the onset of winter 1887 to 1888. Mackay's temperature measurements revealed dramatic improvements in thermal comfort and fuel efficiency. Morning interior air temperature rose to 58 degrees Fahrenheit, while ceiling surface temperature improved to 45 degrees, reducing the thermal gradient from 15 degrees to 13 degrees. More significantly, the stone walls now remained warm to the touch throughout the night, eliminating the cold zones that had previously made corners and wall areas uncomfortable. Wood consumption fell further to approximately 1.5 cords for the winter season, representing a 50% reduction compared to his original 3-cord usage. The neighboring cabin of the Johnson family, still using conventional construction, required 2 3/4 cords during the same period and recorded interior morning temperatures of only 45 degrees with ceiling surfaces at 35 degrees. The envelope thermal mass demonstrated particular effectiveness during severe weather events. When outside temperatures dropped to -15 degrees Fahrenheit during a January blizzard, Mackay's cabin maintained interior temperatures at 50 degrees, while the stone walls continued providing radiant heat that eliminated the need for constant fire tending. Family members could comfortably sit near any wall surface rather than crowding around the stove. The earth berms proved their value during high wind events that had previously created uncomfortable drafts and increased fuel consumption. The dead air space created by the berms eliminated the whistling sounds that had characterized windy nights, and interior temperature remained more stable when strong winds would have previously increased infiltration losses through wall gaps and chinking. By spring of 1888, Mackay had created an integrated thermal system that addressed heat loss through floors, walls, and ceiling while capturing and reusing exhaust heat throughout the cabin structure. The combination of floor thermal mass, wall thermal mass, and envelope improvements had transformed his cabin from a conventional fuel-consuming structure into an efficient heat retention system that provided superior comfort with dramatically reduced wood requirements. The integrated thermal mass system created an unexpected problem during the spring of 1888. Mackay discovered that his stone walls and floor continued absorbing and radiating heat long after the weather had warmed, causing interior temperatures to climb uncomfortably high when outside temperatures rose above freezing. On several March evenings, with exterior air at 15 degrees Fahrenheit, his cabin interior reached 65 degrees, forcing his family to open windows and waste the heat they had worked so hard to capture and store. The issue stemmed from the thermal mass system's inability to discriminate between winter heating needs and transitional season conditions. The stone walls, once charged with heat from the flue passages, continued radiating that energy for hours, regardless of whether additional warmth was desired. Mackay realized that his system lacked controls to regulate when thermal mass was charged and when heat should bypass the storage system entirely. Traditional straight chimney designs offered no solution to this problem. The standard approach provided only one mode of operation. Hot exhaust gases rose directly up the flue and exited immediately, with no mechanism to control draft strength or redirect heat flow based on seasonal needs. During severe cold, this meant wasted heat escape too quickly. During moderate weather, there was no way to prevent overcharging the thermal mass system. Carl Fischer, a Bavarian immigrant who had recently settled near the Platte River, provided Mackay with knowledge of European solutions to draft control problems. Fischer had constructed masonry stoves in Bavaria that incorporated adjustable dampers and multiple flue pathways, allowing operators to control how exhaust gases moved through the heating system based on weather conditions and heating requirements. Fischer explained that Bavarian Kachelofen designs often included what he called seasonal flues, separate pathways that allowed exhaust to bypass the thermal mass during warmer months when heat storage was undesirable. These bypass systems prevented overheating while still allowing the use of the stove for cooking and other purposes. The key innovation was providing the operator with choices about where exhaust heat went rather than forcing it through the same pathway regardless of conditions. Mackay also learned from his own careful observations during the spring overheating episodes. He noted that the thermal mass wall bench from his floor system remained at 80 degrees Fahrenheit well into the morning after moderate evening fires, far too hot for comfort when outside temperatures were rising. The system needed a method to release stored heat when it was no longer wanted, rather than continuing to radiate it automatically. White Pine contributed additional insight during a spring visit when he observed Mackay struggling with temperature control. The Lakota. Craftsmen described winter lodges that used dual flue arrangements, allowing smoke to exit through different pathways depending on seasonal needs. During severe winter, exhaust passed through channels that heated stone thermal mass. During milder weather, smoke could be directed through a more direct route that avoided overcharging the heating system. During the summer of 1888, Mackay designed and constructed a sophisticated chimney control system that addressed both draft regulation and seasonal heat management. The centerpiece was a twin-exit chimney design that replaced his original single flue with two separate pathways of different dimensions. The smaller exit, approximately 6 inches in diameter, created moderate drafts suitable for charging thermal mass during severe cold. The larger exit, 10 inches across, provided strong draft for rapid evacuation when quick heat removal was needed. Mackay installed adjustable dampers at the point where his underground and wall flue systems connected to these chimney exits. Cast iron plates, operated by lever mechanisms, allowed him to control which pathway exhaust gases followed and regulate the strength of draft through his thermal mass systems. During the coldest nights, he could close the large exit and force gases through the entire underground and wall heating network before they escaped through the smaller flue. When rapid heating or cooling was needed, opening the large exit and closing the smaller one allowed direct evacuation. The seasonal bypass system represented Mackay's most sophisticated innovation. He constructed a separate flue channel that connected his stove directly to the large chimney exit, completely bypassing the underground trench and wall thermal mass systems. This bypass included its own damper controls, allowing him to route exhaust directly out of the cabin without heating the stone systems during warm weather when additional thermal storage was counterproductive. The bypass construction required careful engineering to prevent backdraft and ensure proper operation of both systems. Mackay built the direct flue pathway with a slight upward slope and included inspection ports for cleaning and maintenance. The damper mechanisms were designed with positive stops to prevent accidental partial closure that could cause dangerous smoke backup into the living space. Mackay added a heat release system to manage stored thermal energy in the massive stone wall bench. He installed a small register door, approximately 8 inches square, near the base of the thermal mass wall that could be opened to allow convection currents to draw heat from the stored stone mass and vent it outside when cooling was desired. This register connected to a dedicated channel that led directly outside, providing controlled release of excess heat without affecting the main heating system operation. The integrated control system also included modifications to the chimney exit design itself. Instead of terminating vertically, Mackay constructed a short horizontal offset, approximately 2 feet long, before the final upward exit. This offset reduced the direct wind effect on the chimney top that had previously caused freezing problems during severe cold snaps. The horizontal section allowed exhaust gases to retain more heat before encountering the cooling effect of external winds. Testing began with the winter of 1888 to 1889. The dual exit system proved immediately effective during a severe December cold snap when outside temperatures dropped to -20 degrees Fahrenheit. Mackay closed the large exit damper and operated entirely through the small flue, forcing exhaust gases through the complete thermal mass circuit. Interior temperature remained stable at 55 degrees Fahrenheit throughout the night, with thermal mass systems fully charged to provide radiant comfort. During a January warming period when outside temperatures rose to 10 degrees Fahrenheit, Mackay demonstrated the seasonal bypass capability. He closed the thermal mass system dampers and opened the direct bypass, allowing the cabin to cool naturally while still maintaining the stove for cooking purposes. Interior temperature dropped to a comfortable 50 degrees without the excessive heat that had previously made warm spells uncomfortable. The heat release register proved particularly valuable during spring transitions. When thermal mass systems had been charged during cold nights but daytime warming made additional heat undesirable, opening the register door allowed controlled venting of stored heat. Mackay could fine-tune interior temperature by adjusting both the register opening and the damper positions. The chimney offset eliminated the freezing problems that had plagued his original design and those of his neighbors. During the severe cold of February 1889, when several neighboring cabins experienced chimney freeze and smoke backup, Mackay's system continued operating normally. The horizontal section prevented the direct wind chill effect that had previously caused ice formation in chimney tops. By spring of 1889, Mackay had achieved complete control over his heating system's operation. Wood consumption for the winter totaled approximately 3/4 of a cord, representing a 75% reduction from his original 3-cord usage. More importantly, he had created a system that could adapt to changing seasonal conditions while maintaining comfort and preventing the overheating that had characterized his earlier thermal mass experiments. The control system enabled Mackay to operate efficiently across the entire range of Great Plains weather conditions, from severe winter cold through spring warming periods, while maintaining precise control over interior temperatures and fuel consumption. The ultimate test of Mackay's integrated heating system came during the brutal winter of 1890, when an Arctic air mass settled over the northern Great Plains and refused to move for 10 consecutive days. Weather records from the Regional Telegraph Office documented sustained temperatures of minus 30 degrees Fahrenheit for 3 nights running, with daytime highs never rising above minus 10 degrees. Sustained winds from the northwest maintained speeds between 20 and 30 miles per hour throughout the entire period, creating wind chill conditions that made outdoor work impossible and threatened the survival of anyone caught unprepared. Supply chains collapsed under the extreme conditions. The railroad suspended operations when locomotive boilers froze, despite constant firing, leaving homesteaders cut off from coal and manufactured goods deliveries. Local timber supplies dwindled rapidly as families burned furniture, fence posts, and even structural lumber from outbuildings in desperate attempts to maintain interior temperatures above freezing. Several homesteads within 10 miles of Mackay's property reported partial structural damage when water barrels burst, and interior walls developed frost penetration that cracked chinking and split logs. Mackay's neighbors, still relying on conventional heating systems, faced catastrophic fuel consumption during the crisis. The Johnson family to the east burned through 3 full cords of their carefully hoarded wood supply in the 10-day period, yet recorded interior temperatures that dropped as low as 38 degrees Fahrenheit on the worst nights. Mrs. Anderson was forced to move her children into a single room and hang blankets to reduce the heating area when their fuel supply dwindled to less than half a cord with no relief in sight. The Swedish immigrant Eric Svensson, whose Minnesota experience had prepared him better than most for severe cold, still consumed 2 3/4 cords during the Arctic blast. His cabin floor surfaces registered 22 degrees Fahrenheit on the morning of the third minus 30-degree night, forcing his family to lay straw and wool blankets directly on the floor to prevent frostbite during sleep. 2 of his neighbors abandoned their homesteads entirely, moving into the supply barn in town where communal fires could be maintained more efficiently than individual cabin heating. Mackay's system demonstrated remarkable resilience throughout the entire crisis period. His integrated thermal mass network, combined with the sophisticated draft controls, allowed him to maintain stable interior conditions while consuming just 1 3/4 cords total. Interior air temperature never dropped below 48 degrees Fahrenheit, even on the coldest nights, while his thermal mass wall surfaces remained warm enough to provide radiant comfort for his family throughout each night. The performance differential became impossible to ignore when Mackay invited several neighbors to measure and document his cabin's conditions during the worst of the Arctic blast. Using borrowed thermometers and carefully timed observations, they recorded interior temperatures, surface temperatures of floors and walls, and fuel consumption rates that contradicted everything frontier heating wisdom had taught them to expect. On the night when outside temperatures reached their lowest point of minus 30 degrees with 25-mile-per-hour winds, Mackay's cabin maintained 49 degrees Fahrenheit interior temperature, while the thermal mass bench wall registered 68 degrees at its surface. The floor remained comfortable for bare feet throughout the night, measuring 46 degrees Fahrenheit at dawn. Most significantly, the system required only one evening firing to maintain these conditions, with no overnight tending needed due to the heat storage capacity of the integrated thermal mass. Mr. Harris, who operated the local supply barn and building materials store, began conducting his own investigations after multiple homesteaders reported Mackay's impossible fuel efficiency claims. Harris had built his business on supplying standard heating equipment and maintaining inventory based on conventional consumption patterns. Mackay's reported 75% reduction in fuel consumption, if accurate, represented a fundamental challenge to establish supply and demand calculations for winter heating needs. Harris spent 2 days at Mackay's homestead during the Arctic blast, measuring wood consumption, timing firing schedules, and documenting temperature readings throughout the cabin. His records, kept in a ledger that survived in local historical collections, confirmed that Mackay's system outperformed conventional heating by margins that seemed impossible based on accepted frontier heating principles. The economic implications attracted attention beyond simple curiosity about an unusual heating method. Fuel costs during severe winters represented a significant portion of homesteading budgets, often determining whether families could afford to maintain their claims or were forced to abandon them for more economically viable locations. Mackay's dramatic reduction in fuel requirements translated directly to reduced cash expenditures and labor requirements for woodcutting and hauling. Word of the documented performance spread through the regional homesteading network during the spring of 1891. The local settler association invited Mackay to present his methods at their annual meeting, where he displayed technical drawings and shared temperature records from the Arctic blast winter. Rather than seeking patent protection or commercial exploitation, Mackay freely shared his knowledge with anyone interested in implementing similar systems. Several homesteaders began incorporating elements of Mackay's approach into their own cabin modifications. The supply barn started stocking stone lining materials for underground flue construction and damper hardware for draft control systems. Local masons found steady work helping settlers retrofit thermal mass systems into existing cabins, creating a small but growing market for specialized heating system knowledge. The first successful replications appeared during the winter of 1891 to 1892. 3 families within 5 miles of Mackay's homestead reported substantial improvements in fuel efficiency and interior comfort after implementing underground flue systems and thermal mass walls. While none achieved the dramatic 75% fuel reduction Mackay had documented, all recorded improvements of 40 to 50% compared to their previous conventional systems. The technical principles underlying Mackay's success began appearing in regional building guides and homesteading manuals by 1895. Publishers in Omaha and Kansas City included sections on thermal mass heating and underground flue systems in their frontier construction handbooks. The Nebraska Territorial Building Commission incorporated recommendations for thermal mass systems in official homesteading guidance documents issued to new settlers. By 1900, the integrated heating approach had evolved beyond Mackay's original design into multiple variations adapted for different regional conditions and available materials. Homesteaders in timber-rich areas developed systems using stone thermal mass combined with more elaborate wood-burning chambers. Those in areas with abundant clay deposits created thermal mass systems using fired brick instead of fieldstone, achieving similar performance with locally available materials. The long-term legacy extended far beyond the immediate practical applications. Engineering schools in the Midwest began studying the thermal principles demonstrated by frontier thermal mass systems, contributing to the development of more sophisticated understanding of heat transfer and thermal storage in building design. This knowledge influenced the development of improved heating systems throughout the early 20th century. Modern sustainable building movements trace direct lineage to the frontier thermal mass innovations pioneered by Mackay and adopted by prairie homesteaders. Contemporary rocket mass heaters, radiant floor systems, and passive solar thermal storage designs all employ fundamental principles that were proven effective under the harsh conditions of 1880's Great Plains winters. The core lesson that emerged from Mackay's success challenged the basic assumptions underlying conventional frontier wisdom. Traditional methods that had developed over generations in different climates and with different resource availability were not necessarily optimal for Great Plains conditions. By combining indigenous knowledge, immigrant traditions, and careful empirical observation, Mackay had created solutions that dramatically outperformed accepted standard practices while using locally available materials and techniques within the capability of ordinary homesteaders.